Okay, 6.2. So now we're actually going to use the power series that we learned about in 6.1 to actually solve some differential equations, right? And so we're going to start with just second order. In fact, I would say that pretty much every differential equation we're going to solve for the next two sections are going to be second order, right? So second derivative at most, and they're going to be homogeneous. In other words, they're going to be equal to 0. Okay, you can adapt this to a non-homogeneous equation if your g of x, right? If this equals g of x, let's say, and your g of x is an analytic function, which means you can write it as a power series, then you can simply incorporate that into the power series method. But you're not going to see that here. These are going to always be homogeneous, so it'll always equal 0. Okay, so this is our generic second order differential equation. And notice they don't have to have constant coefficients. They could. Yeah, this does not have to be a constant here, right? This should be a0 of x. So that's a typo. It should be a0 of x. Doesn't have to be a constant. Right, so yeah, so the coefficients don't have to be constants. Now typically you want to put this in normal form. In other words, you want to divide both sides by a2 and write it this way, right? So when you do that, your p is just going to be the a1 divided by a2, and your q is going to be a0 divided by a2. Oops, a0 divided by a2, right? And again, this is just a convenient form for us. We want it written this way here. Okay, I know that's weird. Yeah, we want it written the second way with the p's and q's. All right. So the first definition is that a point is going to be called an ordinary. Right. So x0 is called an ordinary point of the differential equation if both p and q are real analytic. Right. So they're analytic functions. They have a power series at x equals 0, right? So basically centered at x0, right? And so if it doesn't, right, if p and q are not analytic at x0, then we call it a singular point, right? So singular points are bad, right? If p and q are not analytic functions, if they don't admit a power series at x0, then it gets complicated, right? Then we may not be able to solve this using a power series. Okay, so for the time being, we're going to stick with ordinary points. In other words, our p and q for this section, right, because we're only talking about ordinary points here, right, so p and q will be analytic functions. And so this method will work, this power series method will work for pretty much all the equations in this section. All right, so let's look at some examples so we know the difference between ordinary points and singular points. So let's start with our first example. Yep, let's just make it y double prime. Oops, sorry. Hang on. All right, y double prime plus 8y prime plus 16y equals 0, right? So notice that this is a 1 in front, so we know p is 8 and q is 16, and these are just constants. Well, constants, of course, are series. It's a very boring series because it's only one term, right? In other words, your c1 x to the 1, c2 x to the 2, those are all 0. So of course these are analytic, right? These are analytic. For all x, right? So this series has no singular points. No singular points. Right? So all points x are ordinary points. Right? And in particular, x equals 0 is where we're going to want to center our series. Right? So in fact, any equation with constant coefficients, right? Constant coefficients, right, have no singular points. They're all ordinary points. Okay. All right, let's look at another one. Suppose we have y double prime minus e to the 3x times y prime plus, let's say, kasha 5x times y equals 0. So again, right, the leading term is 1 here, so a2 is 1, so you don't have to divide by it. It means our p of x is equal to, well, negative e to the 3x, and our q of x is hyperbolic cosine of 5x. And you should remember from the last video that both of these have Taylor series, or Maclaurin series, centered at x equals 0. And they exist for all x, right? So the interval of convergence is from negative infinity to infinity, right? So these are analytic functions. They have a power series, which in the last video we call those Maclaurin series, but they're power series, and so there's no issue here. There's no singular points here either. No singular points. So in particular, right, x equals 0 is an ordinary point, and the interval of convergence will be from negative infinity to infinity. Right? So no big deal there either. Let's go on to another one. Suppose we have, say, x squared y double prime minus 4, that's a 4, sorry, 4xy prime plus 3y equals 0. Okay. So you have to be careful. If you're looking at the negative 4x and the 3, that's not p and q, right? So yes, the p and q, right, the negative 4x is clearly analytic. The 3 is analytic. But remember, in this form, right, you have to have a 1 in front here. This is not a 1. Okay? So this is not in normal form. So to put it in normal form, we have to divide both sides by x squared right? And so in normal form, this is going to be y double prime minus 4 over x y prime plus 3 over x squared times y equals 0. Okay, so now, right, sorry, I mean to do that. This thing here, the negative 4 over x, that's my p of x. And my q of x is 3 over x squared. Okay, so are these real analytic? In particular, at x equals 0, right? We want to center it at x equals 0. Well, clearly not, right? Both p and q do not exist at 0, right? So p and q are not analytic. They don't have a power series at x equals 0. Okay. Now, if you shift this, if you say, what about at x equals 1 or x equals, negative 5? Sure, then you could write these as a power series in that case. But we want to concentrate on x equals 0. And so for x equals 0, they're not analytic, right? So in other words, x equals 0 is a singular point. It's not an ordinary point. Okay. So sure, x equals 1, x equals 2, x equals negative 5. Those are ordinary points, right? So x equals 0 is the only singular point for this equation. Unfortunately, that's the one we care about the most, right? Because there's no reason to, put the center at x equals 5, let's say. Typically we want to use x equals 0 as the center of our series. Okay, so that's what could go wrong, right? Let's do one more quick one so that we can see what else can go wrong here. So example 4, suppose we have, let's say, x squared minus 4 times y double prime, that's supposed to be y double prime, minus 8x y prime plus 7y equals 0. Right? So same issue here. This is not 1, so we have to divide by it. And just divide the whole thing, both sides, right? And when you do that, you're going to get the normal form will be y double prime minus 8x over x squared minus 4 times y prime plus 7 over x squared minus 4 times y equals 0, right? So this is the 4, that's the y. Sorry, they look alike. Right? And so, again, wherever the denominator is 0, that's going to be an issue. So where is x squared minus 4 equal to 0? Well, plus or minus 2, right? So we can say that x equals 2 and x equals negative 2 are singular points. Those are singular points, right? But all other points are ordinary, right? Including x equals 0, right? So specifically, x equals 0 is an ordinary point. Right? But 2 and negative 2 are not. 2 and negative 2 are singular points. Okay? To make things more complicated, you can have imaginary numbers as your singular points. So for example, if this were, let's say, x squared plus 4, then when you set that equal to 0, right, you get x is equal to plus or minus 2i. Right? And those are going to be singular points for that equation. And you might say, well, if they're imaginary, who cares? But this, what could happen is this could affect your radius of convergence. It could affect your interval of convergence, right? Right. So when this was, right, x squared minus 4, you can see x equals 0 is an ordinary point, but you can see that the singular points, 2 and negative 2, might affect your interval of convergence. So your interval of convergence here might only go, say, from negative 2 to positive 2, right? Because at negative 2, you have a singular point. Positive 2, you have a singular point. So your interval of convergence might not be able to incorporate any singular point. Right? And so the same would be true here. If x equals 0 is an ordinary point, the distance from 0 to 2i is still 2. So your interval of convergence might still be the same thing, right? And I say might because it's certainly possible that it could be bigger than that, right? That this series might converge, say, for all real numbers. But when you have singular points, your interval of convergence may not be able to cross those points. Okay, so keep that in mind. Okay, so now we can talk about when exactly do we get a power series solution, right? Well, if you have an ordinary point, then you can center your power series at the ordinary point, right? So this theorem guarantees that. This is theorem 6.2.1, the existence of a power series solution, right? So if x equals x0, so x0, if that's your ordinary point, right, of this differential equation, and keep in mind this is not a normal form, you have to divide by a2. But at this point, right, we can always find two linearly independent solutions in the form of a power series, right, centered at x0. Right? And like I said earlier, for our purposes, this x0 will usually be 0, right? For most of the problems we're going to encounter, we're centering it at 0. Okay? And there might be a few challenge problems where you center it at, say, x equals 3 or something. But, yeah, right? So in other words, your y of x, right, will be a power series of some forms, right? So again, it has to be an ordinary point. If it's a singular point, all bets are off. Then there's no guarantee that you can write it as a power series, okay? But for ordinary points, you can always do that, right? And in fact, you get two linearly independent solutions, right? You get your y1 and y2, right? So you get y1 of x, y2 of x, and then you can form the general solution as a linear combination, right? C1, okay, be careful, right? Capital C1, right? Y1 plus capital C2, Y2. And so that would be your general form of your differential equations. And because it's a homogeneous equation, you're not going to have a particular solution here, right? So yes. So you're always guaranteed that you're able to do this at ordinary points. Okay? And of course, where does it converge, right? So it's going to converge, right, on some interval, right? So this is going to be your interval, right? Where r is the distance from x0 to the nearest singular point, right? And so that's what I was talking about earlier, right? If your x0 is 0 here, and your nearest singular point is at -2 or +2, in fact, they're the same distance away from 0, then that might be your interval of convergence, right? That's your minimum interval of convergence, right? And that'll give you the minimum radius of convergence here is 2. Okay, so it has to converge at least on this interval, possibly bigger, right? It might converge, from -10 to 10, or it might converge for all real numbers. But at a minimum, it's going to converge, right, on this interval here, right? So essentially from negative, so from x0 minus r to x0 plus r will be the minimum interval of convergence. But it might go past that. Okay? So here's a question, right? Example 7. Find the minimum radius of convergence about the ordinary point x equals 0 for this differential equation, right? And I realize this might be too small, so let me rewrite the equation, right? This is going to be x squared minus 4x, oops, there's that 4 again, minus 12, all times y double prime, plus 3 times x minus 5 times y prime, oops, typo, that should definitely be y prime here, right, plus 6xy equals 0. Right, so before we can find the radius of convergence, we have to divide by the a2 term here, right? So we're going to divide everything by this x squared minus 4x minus 12. Right. So that'll give us y double prime plus 3 times x minus 5 divided by, and we might as well factor this, right? This is going to be x minus 4. No, I take that back, right? I guess -6 and 2, right? So x minus 6 times x plus 2. Yep, that works. Times y prime plus 6x divided by the same x minus 6, x plus 2 times y equals 0. So where are the singular points? Once again, the singular points are going to come from where p and q do not exist, right? In other words, where the denominator is 0. And that's going to happen at x equals 6 and x equals -2, right? And that means these are going to be singular points for this equation. So we have 2 singular points, one at 6, one at -2. Okay. Now remember, our ordinary point is x equals 0, so that's where we want it centered at. So what's the nearest point to 0? The nearest singular point to 0 is -2, right? So our minimum radius of convergence can't cross -2. So if we're starting at 0, and we can only go to -2, even though on the right we can go all the way to 6, right? But the nearest singular point is -2, so we can't go past that, right? So in other words, we're going from -2 to 2 again. Right? So that's my minimum interval of convergence, my minimum radius of convergence, because they asked for the radius of convergence. The minimum radius of convergence is 2. Right? Of course, we don't know. I mean, the interval of convergence might be way bigger than this, right? So we're not going to be able to figure that out until we actually solve the series. Right, so that's an example of finding the minimum radius of convergence about an ordinary point, right? In this case, x equals 0. Right. Okay, so I think we have enough information to be able to solve a differential equation using the technique of power series, right? In other words, assuming that we can write the solution as a power series. Okay, so here's our first example. We want to solve y prime minus y equals 0. Don't laugh. I know you know the answer to this. This is about as easy as it gets. We probably did this like in the first week of class, right? So you know how to do this. Just well, by separation of variables, for example. Okay. However, I want to start easy, right? I want to start with a simple equation, one that you actually know the answer to, but we're going to first use this technique of power series to solve this equation here. I mean, why start with a very difficult one, right? So let's start with a simple one and then see how it goes. And again, we can check our answer because you know what the answer should be here. Okay, so y prime minus y equals 0. And this is first order. This is a first order equation. I know we've been talking about second order equations, but you can also use this technique for a first order equation as well. And right, so the way it works, right, the first step when using a power series is to simply assume that that the solution is y equals this power series, right? N goes from 0 to infinity of Cn x to the n, right? Now, remember, we have to make sure that we're centering it at x equals 0 and that 0 is an ordinary point. Well, of course it is, right? Your p of x is 1 and your q of x is negative 1. So there's no issue here. Those are analytic functions, and so you can always, right, all points are ordinary points. And to keep it simple, we're gonna set our solution centered at x equals 0, right? Okay, so that's the first thing you should do. The next thing is, well, we're going to need y prime here. So in other words, we have to take the first derivative, right? So take derivatives is your second step, right? And there's no y double prime in the equation, so we only need the first derivative, y prime. Okay, so remember how to do that. You're just differentiating term by term. So we can differentiate each term separately and then add them up. Right, so you bring use the power rule, right? This is n times Cn times x to the n minus 1. Okay. However, notice I made a mistake here, because if n is 0, then this is going to be x to the negative 1. Remember, you cannot have a negative exponent in a power series, right? It has to start at 0. So that means my n doesn't start at 0 anymore. It starts at 1. Okay, so we're starting at n equals 1 for the derivative. Okay, and remember we start at n equals 2 for the second derivative. Not necessary here, right? Okay, right, so now we want to rewrite so we want to rewrite the equation using a series, right? So we know y prime minus y is going to equal 0. But here's y prime. It's the sum, n going from 1 to infinity, of n times Cn times x to the n minus 1, plus, or I should say minus y. Okay, so minus y, which is just the original series. N goes from 0 to infinity of Cn x to the n. Okay, and remember, this is all going to equal 0 because it's homogeneous, right? Right. And so now you see the problem, right? Here on the first term we have x to the n minus 1. The second term has x to the n. They don't match, right? There's no match here, which means we have to do the reindexing, right? We have to reindex these so that we get a common power of x here, say x to the n, right? So what that means is when you write this out, and maybe we should write out one more time. We'll write it out term by term, right? So when n is 1, we're going to get 1 times C1 times x to the 0 plus, and then n is 2. So 2c2 x to the 1 plus 3c3 x to the 2. And I think you get the idea, right? Oh, let's do one more. Right? So this is going to be 4c4 x to the 3. And then, right, plus dot, 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 right? And then minus, for the second series, this is just going to be c0 x to the 0 plus, well, minus, right, c1 x to the 1 minus c2 x to the 2 minus c3 x to the 3 minus dot, dot, dot. Okay, so notice that there's no danglers here. We're both starting at x to the 0, which means we should be able to write this series starting at n equals 0. Right? So in fact, we really don't even have to reindex, right? If you want, you can call it k, and maybe I'll do that because I know the book tends to do that. So I'll start with k equals 0, but in this case, n and k are the same thing. Okay. Right. Yeah. Okay. Hang on. I think we can do that here. I mean, having written it out this way, yeah. Well, okay. So let's. Yeah. Instead of doing this, let's write out the terms. Again, next time I won't do it this way. I'll just reindex. Right. So for the x to the 0, we get c1 minus c0 times x to the 0. And then we're going to get 2c2 minus c1 x to the 1 plus 3c3 minus c2 x to the 2 plus, and then one more, so 4c4 minus c3 x to the 3. And in general, you write out as many terms as you need to, right, until you see the pattern here. But I think we see the pattern, right, or at least I hope we do. Now we can write it as a formal summation, and again, I'll use k. So k goes from 0 to infinity, right? And what's in the parentheses here? Well, we have c1, but if we're starting at 0, then this is going to have to be k plus 1, right? And you notice that it's, for the next term, it's 2 times c2. So in other words, you're going to have to multiply this by k plus 1. So I should have done that first, right? So k plus 1 or k minus 1. So if k starts at 0, right, this is going to be k plus 1. And then this is 1, right? So yeah, 0 plus 1, k plus 1 times ck. So I think that takes care of the first one, right? And then the minus, well, this is just minus ck, right? So if k is 0, minus c0. If k is 1, it's minus c1, and so on, right? So this is all times x to the power k. Okay, are you okay so far? So again, you have to look at the first terms here. Maybe I'll use this, right? So for these terms here, that gives you this. And then for the second term in each bracket, in each parentheses here is this. Right? So I think that works out. Okay, now what? Well, remember, this is just another name for y prime minus y, right? So this is all just y prime minus y, which from the original differential equation, that equals 0, right? So this has to equal 0. Okay, now if this function equals 0, right, for all x, or for all k rather, then the only way that can happen is if these coefficients are all equal to 0, right? That was the identity principle originally that we did in the previous video, right? In 6.1, I think I mentioned, right, the following property here, that if you have your Cn x to the n, if this is equal to 0, that means that Cn has to be 0, right, for all n. And so that's where this is going to be useful here. All of this stuff in here, this is my Cn now, right? It's a mixture of ck's and ck plus 1, but it's my general Cn, right? It's the number in front of the x to the n, or x to the k in this case. Right, so let's see what happens then if we set this, right? This is k plus 1 times ck, ck plus 1, k plus 1, minus ck, that has to be 0, right, for all k, right? Well, remember, k starts at 0, so 0, 1, 2, 3, and so on. So for non-negative integers, k. All right, so what can we do with this, right? Well, we can rewrite this in terms of, right, so we want to solve for ck plus 1, right? So we can add the ck to both sides. Add ck to both sides. And then we just get k plus 1 times ck plus 1 is equal to ck. And now I can divide both sides by k plus 1. Right. So that gives me the following equation, that ck plus 1, right, the k plus first term for the c's, is just ck divided by k plus 1. Okay. Now, obviously, this is not the solution, but this is a very important equation, right? It's a relationship between the various values of c, right? Some in terms of ck, some in terms of ck plus 1. In some equations, you might have ck plus 2, right? But in this case, this is a relation between the c's. And so we call this a recurrence relation. Recurrence relation. I think I'm spelling that right. That's an E, right? So this is going to be the key to solving our equations. You have to get the recurrence relation, right? Okay, so so that's basically step 3, is to get the recurrence relation, right? So all of this was step 3 here, and we got the recurrence relation. Now, what do we do with that? Well, if it's not obvious what the c's should be, let's write out a few of these terms here, right? So let's start with k equals 0. So let's start with k equals 0, right? We just get k plus 1 is, well, c1, and that's going to be c0 divided by 0 plus 1 is 1, right? So this tells me that, hang on. This tells me that c1 equals c0. Right. So let's go on to k equals 1. Right? So 1 plus 1 is 2, so this is c2 is equal to ck, which is c1, divided by k plus 1. 1 plus 1 is 2. So that tells me that my c2 is just c1 divided by 2. Right? Let's do one more. Let's go on to k equals 2. So that tells me that c3, right, 2 plus 1 is 3, is equal to ck, which is c2, divided by 2 plus 1, which is 3. Right? So that tells me my c3 is c2 divided by 3. Right? And I think you see the pattern here, right? My c4 should be c3 divided by 4, and so on, right? But remember, c1 is the same as c0, so this is really just c0 divided by 2. And what's c2? c2 is c0 divided by 2, right? So this is 1 over 3 times c0 divided by 2, so that's c0 over 6. And, right, so this is going to be 1 over 4 times c3, but this is my c3. It's c0 over 6. So this is c0 over 24. And so on, right? So what is c0? c0 is just an arbitrary constant, right? It's just a number, arbitrary constant. Right? So you're always going to get at least one of your, right, c0 or c1 maybe, some just arbitrary constant. We don't know what that is, right? But all the other c's, c1, c2, c3, are in terms of the c0. Okay? See that? And so I don't know if you recognize this 2, 6, 24, but if we get one more, you might recognize it, right? So this is going to be c4 divided by 5. And think about what we did here, right? We did 1 over 5 times 1 over 4 times 1 over 3 times 1 over 2 times 1 over 1, c0, right? So this is 5 times 4 times 3 times 2 times 1. That's just 1 over 5 factorial times c0. right? We could have written C4 as 1 over 4 factorial times C0. This is 1 over 3 factorial times C0. This is 1 over 2 factorial times C0. And this is 1 over 1 factorial times C0. So, right, so now if hopefully you see the pattern that the Cn plus 1 is really just Cn divided by n factorial. Okay. So is that right? So the recurrence relation, right? If you're clever enough, or if you write out the first few terms, you might be able to figure out the Cn in terms of the C0. Oh, C0. I'm sorry. Yeah. No, this is not Cn anymore, right? This is C0. Right. Yeah, the Cn is for the recurrence relation. Right. So yeah, this is C0 now, right? Oh, wait a minute. Oh, I didn't need to add one here. So this is also wrong. This is just Cn, not Cn plus 1. See, I was getting confused between the recurrence relation and the closed form of the C's, right? So this is now a closed form of C's. This is called the closed form, right? So now we can find C for any n, right? We know that C of C13 is just going to be C0 divided by 13 factorial, right? Right. We don't have to write it in terms of C12, C11, C10, and so on. Okay. Anyways, yeah, so this is going to be important. Cn is equal to C0 over n factorial. Why is that important? Because, well, right, this is our Cn now. So go back to the power series. Going back to our power series, remember our y was written as the sum, n going from 0 to infinity, of Cn x to the n. But now we have a formula for Cn. Right? This Cn is, well, let's write it out. Right? It's C0 divided by n factorial times x to the n. Now, the C0 is a constant. We can just bring that outside. And now we have the sum going from n equals 0 to infinity. Let's just write it as x to the n divided by n factorial. Right? So there's our solution, right? This is now y of x, right? So we answered the question. We have C0, which is an arbitrary constant, times the sum going from 0 to infinity of x to the n over n factorial. Okay, so we're done. This is the answer. Now, you might say, well, but it's written as a power series. Well, in some cases, that's sort of the best you can do, right? Right? In some cases, you just have to be content with the fact that it's a power series, and, you know, this might not be in terms of some other function that you know about. Now, of course, it is in this case. All you have to do is go back to 6.1, and, you know, I hope you remember this. Yep. Right. This here, we just did it in 6.1, right? This is just e to the x. This is the Maclaurin series for e to the x. So this is C0 e to the x, right? And remember earlier I said that, that you already knew the answer to this equation. Right? Remember the equation was y prime equals y, or y prime minus y equals 0. And of course you solved that using, well, originally we did it by separation of variables, right? I think that's the easiest way to solve this, right? So obviously this is not the easiest way to solve it by any stretch, right? This took a long time to get the solution using a power series. So not the most elegant way of doing it. Clearly, I would think you would probably, given the choice, you would prefer to solve this by separation of variables, and I would agree with you. That's the way to go here, right? So the C0, you can just relabel it as C, right? You don't have to call it C0, although that's, you know, that's what it is, right? That's the C0 in the term here, right? Okay, so yes, so in this case we get a nice form for the answer that we already knew that it was going to be C e to the x, right? But that won't always happen. In other words, this might be some weird looking series and you might not recognize it, right? You might not recognize it as, sine of x or log of x plus 1 or something. And in that case, you just leave it as a series, or in some cases, it might be beneficial to write out what it is, right? So this is just going to be C0, right, times x to the 0, right, plus C1x plus C2 over 2 times x squared plus C3 over 6 times x cubed plus C4 over 4 factorial, which is 24, times x to the 4th, and so on, right? You can write out as many of these as you need, right? And of course, this now, if I terminate the series, if I leave it as x to the 5, well, this is not the full answer anymore, because the full, right, this is the full series, the power series that goes to infinity, right? However, this is a good approximation to the series, right? And the more terms you write out, the better the approximation, right? So, of course, if you want the exact answer for the series, you would have to say that, this keeps going forever. Okay. But yes, to sort of get a handle on what this weird series, and in some cases it's going to be a lot weirder than this. It's going to, involve, -1 to the n plus 3 divided by, n minus 5 factorial times, just a weird, convoluted type series here. And in that case, just write out maybe the first 4 or 5 terms, and for the most part, that's sort of a practical way to write the solution in many cases. It's just, it's because this is a nice, easy example that we started with, y prime minus y equals 0, right, that we can actually write this as, a closed series in terms of a familiar function, e to the x, right? Or in some cases, it might be sine x or cosine x or hyperbolic cosine of x or something like that. But to be fair, in most cases, you are not going to recognize this as a familiar series as we could in this case. Okay. So like I said, I just wanted to start out with a simple equation, and that's how this works here. Before moving on, where were we? So step 3 is to get the recurrence relation, and then step 4, right? So our step 4 here was to write, using the recurrence relation, to write the answer as a power series, right? And that might involve writing it as a closed form, not for a function, but the infinite series using the sigma notation, or in some cases it might involve just writing out the first 4 or 5, or in this case 6 terms of the series. So that's your step 4. Okay, and so to recap, step 1, assume that you have a power series as a solution. Step 2, take all the derivatives you need. Step 3, reindex, right? Or if in this case we didn't have to reindex, but we had to sort of write it all as a single series instead of 2 separate series here. We want to write it as one series. And then because it equals 0, you set that coefficient to 0, and that gives you your recurrence relation. Right? And then you have your recurrence relation, and then again, sometimes you might have to write out a few terms to get the pattern. And if you don't see the pattern, right, if you can't write it as a closed form like this, well, then you just leave it in terms of these numbers here, and then write out, the first few terms. Okay, so that's going to be our method for solving power series in general. Okay, I think we should do one more, because like I say, that one we just did was, very simple. And once you get to second order equations with y double prime, it's not going to be as nice as that. But the procedure is the same. In fact, let me bring up the process here. Okay, right. So this is the method for finding a series solution, the series solution method, right? And we're solving a second order equation about an ordinary point, right? And you notice in this case here, let me write down the equation. So as we look at step 1, here's the equation, y double prime minus x times y prime plus 2y equals 0. Oh, this is number 10 in the book, right? So this is a pretty typical example that we're going to have to solve using a power series. And notice that they want us to write it to order x to the 7. So they want us to write out as many terms until we get x to the 7. Okay. All right. So step 1, assume you have a power series centered at x equals 0, right? And of course we know that 0 is an ordinary point here, right? We're not dividing by anything here, right? The leading coefficient is 1. So in normal form, this is already in normal form. Our normal form, p of x is negative x, and q of x is equal to 2, and these are both analytic. So that tells me that x equals 0 is an ordinary point, right? Right, and so that means we can assume that we have a power series solution. Y is going to be the sum, n going from 0 to infinity, of Cn x to the n, right? Right. Again, you always start at 0. Right? In some cases, it might not start till 1 or 2, but that will become clear once you actually write out the recurrence relations and so on. But until then, always assume you're starting at n equals 0. Okay. Okay, so what do we need? Well, the equation involves the first derivative and the second derivative. So now we need to take two derivatives here. I wonder if I can squeeze them in here, because we did these already, right? We did y prime, which is the sum n going from 1 to infinity of n Cn x to the n minus 1, right? And then for y double prime, this was the sum n going from 2 to infinity of n times n minus 1 times Cn times x to the n minus 2. I think I just made it. Great. Okay, so I'm going to need all three of these, the first derivative, the second derivative, and the original function. Okay, so now step 2, right? Okay, so this is part of step 2. We took the two derivatives. Now we have to plug them into the differential equation. The differential equation, again, being y double prime minus xy prime plus 2y equals 0, right? And so what's y double prime? Well, it's the sum, n going from 2 to infinity, of n times n minus 1 times x to the n minus 2, right? Minus x times y prime. Well, y prime is n equals 1 to infinity of n times Cn times x to the n minus 1. Now be careful here. I put the x on the outside, but that really belongs on the inside here. Hang on. That goes over here, right? So this is x on the inside, x to the 1. So notice what happens. X to the n minus 1 times x is x to the n minus 1 plus 1, which is just x to the n. Okay? So yeah, this is really, if I get rid of the minus 1, this is really just x to the n here. Right. So you see what happened. This x on the outside of the, or minus x I should say, the minus x, when you combine that with the series, the n minus 1 changes to n. Right. Because you're subtracting 1, then you're adding 1, and that just makes it x to the n. So I hope that helps. All right. And then plus, we have 2. Now, the 2, again, can go on the outside. But just to make it easier, I'm going to put it on the inside. And this, I'm sorry, here. This was just Cn x to the n. Okay. So our goal is to combine all of this, right? Remember, all of this equals 0, but we have to get it all into a single series. We have to write this into a single series. Yep. Oh. Right. Single series. Oh, I'll start all the way on the left here. Right. You need a lot of space. And n, well, oh, not n anymore, k, because we want to reindex, right? We want to reindex to k. All right, so now where does k start, right? Where are we going to start our k? So for our x's, what's the lowest power that's going to be involved in each one of these series, right? What's the lowest power of k for all of these? Okay, so obviously for the last term here, we're going to get x to the 0, right? But notice this middle term, we only get x to the 1. For the first term, we get, right, x to the 0, because this is 2 minus 2 is 0, right? So even though the first and the last start at x to the 0, this middle term only starts at 1. So that tells me that I have to get the x to the 0 separately. So let's start with the term on the left here. When n is 2, you're going to get 2 times 2 minus 1 is 1 times x to the 0. Okay. What about this last one? This last one is just going to be plus 2 times c0 times x to the 0. Okay, but the middle term is going to be x to the 1. So these are going to be sort of left separately here. Now we can start our sigma series with, again, I keep doing n, but this is going to be k equals 1 to infinity. So that's going to be common to all three of these, right? Okay. So what's going to happen if we want to start at k equals 1? How do we reindex the first series? Because the first series is x to the n minus 2. Okay, so remember our goal. Our goal is to get x to the k here, right? All of this will be multiplied by x to the k. It's going to be multiplied by some big thing here, and that's going to be the cn, right? Or ck in this case, right? So, yeah, so if we want this exponent here, this n minus 2, we want that to be k now, right? So k is n minus 2, right? Which means n is k plus 2, right? Okay. So, right, so if n is k plus 2, this is going to be k plus 2, right? And n minus 1 is k plus 2 minus 1, or k plus 1, right? I forgot something here, right? I forgot the c's. Oh boy. Shoot. Well, let me see if I can fix that here, right? So there should be a c what? A cn, oh, this is the second derivative, right? Yeah, I think this is just cn here. Yep. See, I forgot the cn. This cn here should go right here. Oops. Better late than never, right? So if that's cn, this will be c, let me use the same color, ck plus 2, right? So yeah, times c sub k plus 2. And then x to the power k, right? And minus 2 plus 2 is k, right? Okay, phew. I'm glad I caught that, right? Now, what about the second series? Remember, the second series, there's a minus in front here, so that's going to be minus. And we want x to the k. So if this is k, then, well, n is k. K is n, right? So this is just k equals n. So that's nice, right? We're still starting at 1 to infinity. So this will just be k times ck times x to the k. So not much going on here, right? Plus, and then again, k starts at 1 to infinity. Remember, we already took care of this c0. That's over here on the left, right? This 2c0x to the 0. So we already have that. So if we're starting at 1, and this is going to be x to the k, and we have x to the n, well, same thing. We might as well just call it k instead of n, to be consistent, right? So this will be 2 times ck times x to the k. Right? And remember, this still equals 0. But now we can combine all of this into a single series and a single summation. Sorry about that. And so to do that, well, first we have to write the first two terms here. This is just going to be 2, you know what? If I forgot this, I forgot the C here too, right? This has to be, what, C0. Wait, was it C0 or, so where did this one came from? The first term here, right? The 2 times 1, yeah. Yeah, so this was C0 and this was C0. No, this was Cn. We're starting at 2. Oh, gosh. So you can see how confusing this is, right? We're starting at n equals 2, so that means this Cn here, this has to be C2, not C0, because we're starting at 2, right? So this is 2 times C2 plus 2C0, right? X to the 0 is 1, right? So, let me try that again. This is 2C sub 0. Okay, so those are the first two terms that we have to write separately. Plus, and now let's see if I can combine everything here. So k starts at 1 and goes to infinity. And what are the coefficients? The coefficients are k plus 2 times k plus 1 times, and I nearly missed it, ck plus 2. We have to include that, right? Essentially, we're factoring out the x to the k here, right? So the next one will be minus k times ck. Oop, I was going to write x to the k, but we're factoring that out. And then finally, plus 2 times ck, and then all of that times x to the k equals 0. Okay, so I think that's right so far. Right. So if all of this equals 0, what has to be true? Well, all of this coefficient of x to the k, that has to be 0, right? This has to equal 0. But this also has to equal, right? Everything has to be 0, right? So first, let's write the first two terms here. 2c2 plus 2c0, well, that's 0. And so 2c2 is negative 2c0. And if you divide by 2, you just get that c2 is negative c0. Okay. Keep that in mind. That'll come up later. But now let's take care of the whole big series here. All of this, right? So I'll write it all out again. K plus 2 times k plus 1 times ck plus 2 minus, and I think we can combine these, right? This is going to be minus k minus 2. I'm wondering if I should do plus 2 minus k. Nope. I'll leave it as minus k plus 2. Oh, sorry, k minus 2. Right, because it's minus a negative. So k minus 2 times ck, right? That has to, this all has to be equal to 0. Okay? So this is going to give us our recurrence relation, right? We're going to solve for ck plus 2 in terms of ck. Right? So how do we do that? Well, let's add this term to both sides. So on the left we get k plus 2 times k plus 1 times ck plus 2 equals k minus 2 times ck. Okay, so I just added the second term to both sides. All right, now just divide everything that's not ck plus 2. So we're going to divide by k plus 2 times k plus 1. Okay, so these cancel. And we have our recurrence relation, which I'll write over here, ck plus 2, that's going to equal k minus 2 divided by, and you could multiply this out, but I'm not. I'm going to leave it as k plus 2 times k plus 1, all times c sub k. Okay, so that is our recurrence relation. If I can spell, recurrence relation. And so this is going to tell us what, our C1, C2, C3, and so on are, right? So what is our arbitrary constant? Our arbitrary constant will be C0, right? So we have C0 is arbitrary. And we already know that C2 is just negative C0, right? That was from the first two terms, the danglers that I call them. from, out in front, right? And so now we need to figure out what C1 is. Well, since that's where we're starting, right, we're going to start at k equals 1 now. At k equals 1, notice that we can't write C1, we can't start with, k plus 2 equals 1, because then that would mean k is negative 1. So we can't go less than 0, right? So 0 is where we're starting from. So our C1 then is also going to have to be arbitrary. So both C0 and C1 are arbitrary. Okay. So yeah, so if we start with k equals 1, then k plus 2 is going to be 1 plus 2 is going to be 3. So this will tell us what C3 is in terms of C1. So if k is 1, k minus 2 is negative 1, divided by 1 plus 2 is 3, and 1 plus 1 is 2, times C1. Make sense, right? Which of course is just negative 1 over 6 times C1. Okay, moving on, let's do C4, right? C4, so that's going to happen when k is 2. So when k is 2, we're going to get, 0, right? 2 minus 2 is 0. 0 divided by, whatever, right? It's 4 times 3, but it doesn't matter, right? Times C2. So this is going to be 0 times C2, which is 0. Okay, so C4 is 0. Right? C4 is 0. Right? Let's go on to k equals 3. So that's going to give us C5. When k equals 3, this is going to be positive 1 over 5 times 4 times C3. Right? But remember, C3 was, so let's leave it as this, 5 times 4, and then C3 was negative 1 over 6, which was 3 times 2 times C1. Right? So you can see this is going to be negative 1 over 5 times 4 times 3 times 2. That's going to be 5 factorial, right, times C1. Right? Let's keep going. Right? Until you're absolutely sure you know what the pattern looks like. Let's get C6, which is k equals 4. So what's that going to be? That's going to be, there's my recurrence relation. So 4 minus 2 is 2, divided by 4 plus 2 is 6, 4 plus 1 is 5, times C4. But hang on, C4 was 0, right? So whatever this is 1 over 15 times C4. Well, 1 over 15 times 0 is 0. So C6 is 0. All right, let's do one more. I think we might need one more just to make sure. So this will give us C7. And that's going to be, if k is 5, 5 minus 2 is 3, so the numerator is 3. The denominator will be 7 times 6 times C5. Okay, so this is 3 divided by 7 times 6 times C5, but C5 is negative 1 over 5 factorial times C1. So it looks like we're going to get negative 3 divided by 7 factorial, right? So this is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So 7 factorial times C1. Okay. I want to make sure that that's 3 there. Yeah, I think that's right. Right, so I think we see a pattern here, right? This is just going to be, k plus 2 factorial in the denominator. Now, it might not be clear what the numerator is at this point, so, it's debatable about whether or not we want to continue. After all, remember, we're supposed to get this up to x to the 7. So once you have C7, that should be enough, right? That should be enough, to get, to write out, 7 terms, or actually 8 terms if you're starting at 0. So if n is 7, that means it's 8 different terms here. So I don't think we need the next one, but, well, actually the next one's easy, right? You see the pattern here. This has to be 0. All the even c's have to be 0 here, right? So to get k equals 7, this is going to be C9, which is going to be, let's see, 7 minus 2 is 5. So this will be 5 divided by 9 times 8 times C7. And C7 was this, right? So this is going to be 5 times negative 3 divided by 9 factorial times C1. Again, C1 is the arbitrary constant. So yeah, this could go on forever here. You know, this is just negative 15 divided by 9 factorial. That's a 9 times C1. Right? All right, so now we just have to write out the series. And so let's do that down here. Right? So we're going to get y is equal to the sum n going from 0 to infinity of Cn x to the n. That's our usual power series. And what are our n's here? Well, let's start with C0. Remember, C0 was arbitrary. So this is just going to equal C0 times x to the 0, right? Oops, let me make that clear. This is C0. And then plus C1x. What's C1x? Well, remember, C1 is also arbitrary. So this is just going to be C1 times x, right? Plus C2 times x squared. Now, I wrote this out already, but what's C2? It's just negative C0. So this is just going to be minus C0 x squared. Plus, what's the third term? The third term will be C3. And what was C3? C3 was negative 1/6 times C1. So this will be, this will be negative again. Negative 1/6 times C1 times x to the 3. Right. Remember, we want to get to x to the 7. So we got to keep going here. What's going to be x to the 4? Well, C4 was 0, so we can skip that term, right? There's no x to the 4 term. What about x to the 5? When c is 5, we have negative 1/5 factorial C1. So that's going to be negative 1/, I think it's 120, right, times C1 times x to the 5. And, right, C6 is 0. So there's no x to the 6 term. So we go on to the x to the 7, which is, k is 5, but n is 7, right? So C7 is just going to be this big number here, 3/7 factorial. Well, I don't know. I'm doing this quickly. I'm getting what? Oops, sorry. Move that back up. I'm getting 1/1680. 1,680 times C1 x to the 7. And that's not what the book got. I think the book got half of this. Am I missing a 2 here? No, this 2 was k minus 2, so that's right. So this is C7. Let me make sure I did C7 correctly. I got 3. So the 3 is from 5 minus 2. And then k is 5, so this is 7 times 6, so that's right. And then C5 already had the 5 factorial, so this is 7 factorial. No, I think it's right. It's just the 7 factorial. Let me try that one more time. And just skip the 3. Yep, 1680. Okay, well, I think that's it then. Of course, this is not the complete solution. There's also the plus ... because this goes on forever. But remember, they wanted us to write out just the first 7 terms, the first 8 terms, to order x to the 7. And so again, maybe not a very satisfying answer in the sense that, well, what is this function? Is this, cosine of x, or is this, some weird inverse hyperbolic tangent of x, or some weird function? Possibly, but it's not obvious, right? It's certainly not obvious to me what the full pattern here is, and if this indeed represents some function. But right, so remember earlier I was saying, well, this is sometimes the best you can do, is just write it as a series and write out the first 5 or 6 or 7 terms, although some of them are 0, right? And in fact, what you could do, of course, is collect your constants here, right? So hidden in this series is 2 linearly independent terms. So let's write those out, right? Let's write those out. So this is going to be C0 times 1 minus x squared, right? And then plus C1 times, well, everything else, right? So we have an x, we have minus 1/6 x cubed, minus 1 over 120 times x to the 5, minus 1 over 1680 times x to the 7, and the next term is probably minus, but unless you get the x to the 9, well, we do have x to the 9th, right? It's this one here. It's negative 15 over 9 factorial, whatever that number is. So negative 15 over 9 factorial times x to the 9th, right? Plus dot, 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 even though it's probably a minus, right? So there you go, right? There's your complete series solution. Y of x is equal to this, right? And you can call this C1 and C2. That's the way we used to do it. But right, this is our y1, right? So our y1 is really just a polynomial, 1 minus x squared, right? So when that happens, we say that the series terminates, right? It terminates. It doesn't. It ends, right? It doesn't go on to infinity. In other words, right, what happens is the even part here, the x to the 4, x to the 6, all those c's are 0. Okay, so your first linearly independent function is just 1 minus x squared. And your second one, your y2, is everything in parentheses here, right? X minus 1/6 x cubed, x cubed, minus 1 over 120 x to the 5, minus 1 over 1680 x to the 7, and so on, right? Goes on forever. So this series does not terminate, right? This is a power series, an infinite series. Okay, right, so our full solution then is, again, just to be consistent, I'll call this C0 y1 plus C1 y2, but, whether you call them C0 or C1 or C2 doesn't matter, right? The point is we have 2 linearly independent solutions, and when you combine them, you get your full general solution, for the original equation. Okay. And so that's the power series method here, right? It's, again, maybe some of you are thinking this is not very satisfying because I can't wrap my head around the series. It's not sine of x or e to the negative cosine squared of x or some, it might be a complicated function, but it's still a function that you recognize. This, of course, might be a function that eventually, if you get the pattern, you might be able to find it, but for our purposes, we're going to have to leave it at this, right? We're going to have to leave it at this and just be satisfied that we can write out as many terms as we want, right? If we need more terms, x to the 11, x to the 13, x to the 15, you can always calculate them. You just have to keep going with the recurrence relation here. Just, keep going, k equals 8, k equals 9, k equals 10, and so on. And then you'll get more terms in the series. In other words, you can make this as precise as you want, right? When you stop the series as we did here, then it's an approximate answer. It's approximate solution. But it's probably a very good approximation when you have x to the 7 or x to the 9. And the more terms you have in your series, the better the approximation. And of course, a computer can do tons of these series here, it can write it out to x to the 100 or x to the 1,000, and that'll give you a very precise answer. So what I'm telling you is you might have to get used to the idea that in some cases you just have to deal with, a power series, or if you want to deal with an approximate solution, you deal with some sort of a polynomial here to some degree, nth degree, 9th degree, 10th degree, whatever you want to end at, or however precise you want it. So really we should rejoice, right? We did solve the equation, right? Remember the original equation, I almost forgot, is y double prime minus xy prime plus 2y equals 0, right? So this was the original equation. I think it was y double prime, right? Minus xy prime plus 2y equals 0. Right? None of the techniques that we learned way back in chapter 4 can deal with this, right? This is not a Cauchy-Euler equation. If you remember the Cauchy-Euler equations, we had a very specific pattern here, right, where we had, right, the exponent has to match the order of the derivative, right? So when we had that, we were able to use our technique here, x to the 0 is 1, right? So this is just y equals 0. Yeah, so this is Cauchy-Euler. So this was, I think, the only very specific form of an equation where we had non-constant coefficients that we were able to solve in chapter 4, right? So these were the Cauchy-Euler, right? And of course now we can solve it by power series, but if you recognize it as a Cauchy-Euler series, Cauchy-Euler equation, then there's no reason to use a power series because, that could take you a lot longer, but you should end up with the same answer that you get with the Cauchy-Euler equation. In fact, if you remember, the Cauchy-Euler, right, you're assuming, a solution of, say, cx to the m, right? In other words, it's going to be, some power function. So it's going to be a series that has only, one non-zero c, or maybe two non-zero c's, right? So it might be, c1 x to the 2 plus c2 x to the 5. And so all the other c's, right, for x to the 0, x to the 1, x to the 3, x to the 4, x to the 6, x to the 7, all those c's will end up being 0. So of course the series terminates and you just get a two-term polynomial. So again, that's Cauchy-Euler. I'll let you review that for chapter 4. But the point is this equation here, the one that we just solved, is not Cauchy-Euler. It doesn't fit into that form. And in fact, most of the equations that we get that are non-constant polynomials will not be able to fit that way. Right. And obviously, if it weren't for this x here, if this was just minus 1, then this is a constant coefficient polynomial. Then, of course, you can use chapter 4 for that. But because of that x, that kind of ruins it, right? So now the only way to solve these, at least that we know of, the only way we know how to solve these is by using a power series. So hopefully that's enough. I know I just did the 2 examples, and you can see that each one of these takes a considerable amount of time and effort. And so all I can say is, do at least one, and see if you can do 2 or 3 from the homework, because these are going to be on your next problem set, which, well, I'm not going to mention it here, but your problem set 7 will basically be from chapter 6, and I will announce when that happens soon on Blackboard. But so I hope this helps. It's very tedious, right? It's a lot of sort of grinding through the k equals 1, k equals 2, k equals 3, and just, getting as many terms as you need. In some cases you might just want 3 or 4 terms. Generally speaking, I would insist that at least 5 terms, right? So at least go to x to the 4. But probably better you go to x to 5 or x to the 6, or in this case x to the 7 was where we wanted to end up. And that should do it. That's 6.2. Again, Remember, this is the method you're using here, the series solutions method. And remember, you have to have an ordinary point. So our x equals 0 here, right? We established right here, we established that it is an ordinary point. If it's not an ordinary point, well, then this method may or may not work. In fact, that's the next section. 6.3, we'll talk about another method. Well, it's still a series method, but that's going to be for some type of singular points. So remember when I said that when you have a singular point, there's no guarantee that it's going to work. But it turns out that it will work in some cases. So that'll be next.